FastMCP 2 implements a distributed task scheduling system through its integration with Docket, enabling asynchronous execution of long-running operations while maintaining progress tracking and worker management capabilities. The framework's dependency injection system provides direct access to task coordination primitives, allowing developers to orchestrate background work and monitor execution state through protocol-native MCP interfaces. We're about to examine how a task-enabled function leverages these scheduling mechanisms, demonstrating the initialization of progress reporting, worker metadata access, and dynamic task submission through the Docket interface. The code reveals how FastMCP's decorator-based approach transforms standard async functions into distributed workflow components while maintaining clean separation between business logic and execution coordination.
From Docket, import Docket, worker. From FastMCP, import FastMCP. From FastMCP dependencies, import progress, current Docket, CurrentWorker. MCP equals FastMCP my server. At MCP, tooltask equals true. Async def my task. Progress equals progress. Docket equals current Docket. Worker equals CurrentWorker. SDR, hash schedule additional background work. Await Docket, add another task, arg1, arg2. Hash access worker metadata. Worker name equals worker name. Return done.
This code demonstrates FastMCP's advanced task scheduling and worker management using Docket's dependency injection system. The myTask function is registered as a background task with task equals true, enabling it to run asynchronously while supporting progress reporting and additional task scheduling. Through dependency injection, it accesses three key components: progress for client feedback, current Docket for task coordination, and CurrentWorker for worker metadata. The pattern showcases how FastMCP integrates with Docket's workflow engine, allowing tasks to schedule additional work via Docket.add while maintaining context about the current execution environment. This approach enables complex workflow orchestration where tasks can chain operations, access worker information, and report progress, all through protocol-native MCP background tasks rather than application-level concurrency primitives. The design trade-off here is between simplicity and power. While you could use raw Asyncio or threads, this Docket-based approach provides built-in progress tracking, distributed execution, and MCP protocol compliance. The in-memory backend offers zero configuration simplicity for development, while Redis enables production-scale persistence and horizontal scaling. The dependency injection system cleanly separates task logic from execution concerns, making the code more maintainable while supporting advanced features like retries and timeouts through Docket's API. Let's break it down.
From Docket, import Docket, worker.
Imports the Docket and worker classes from the Docket module, providing access to FastMCP's dependency injection system and worker management capabilities.
From FastMCP, import FastMCP.
Imports the FastMCP class from the FastMCP module, which provides the core functionality for implementing Model Context Protocol MCP servers. The imported class will be used to create MCP server instances with customizable identifiers.
From FastMCP dependencies, import progress, current Docket, CurrentWorker.
Imports three FastMCP framework classes: Progress for task progress reporting, current Docket for accessing the active Docket instance, and CurrentWorker for retrieving worker information. These dependencies enable task coordination and worker context access within FastMCP functions.
MCP equals FastMCP my server.
Creates an instance of FastMCP with the server identifier, my server. The string parameter serves as a label for the server that will be visible in MCP protocol handshakes, allowing clients to identify this specific server instance. This line initializes the MCP server with the given name, but doesn't configure any operational behavior or functional parameters.
At MCP, tooltask equals true.
Decorates the following function as a FastMCP tool that can be invoked as a background task. The task equals true parameter explicitly marks this tool for asynchronous execution, enabling progress reporting and dependency injection via Docket.
Async def my task.
Defines an asynchronous function named myTask with an opening parenthesis, indicating the start of its parameter list. The function is declared as a coroutine using the async def syntax, allowing it to use await expressions for non-blocking operations. The line ends with an opening parenthesis, suggesting parameters will follow in subsequent lines.
Progress equals progress.
Creates a progress instance using the default constructor and assigns it to the variable progress. This establishes a progress reporting mechanism that can be used to track and communicate task completion status.
Docket equals current docket.
Declares a variable docket of type docket and initializes it with a new instance of current docket. This creates a docket object that provides access to FastMCP's dependency injection system within the current execution context.
Worker equals CurrentWorker.
Creates a variable named worker of type worker and assigns it the result of calling CurrentWorker. This retrieves the CurrentWorker instance from the FastMCP context, providing access to worker-specific information and capabilities within the task execution environment.
Await docket. Adnauthor task arg1 arg2.
Asynchronously schedules a new task named another task to be executed by the docket, passing arg1 and arg2 as arguments to the task. The add method of the docket handles the task registration, and the await keyword indicates this operation is non-blocking, allowing other code to execute while the task is being queued.
Hash access worker metadata. Worker name equals worker name.
Retrieves the name property from the worker object and assigns it to a variable called worker name. This captures the worker's identifier as a string for potential use in logging, debugging, or protocol handshakes.
Return done.
Returns the string literal done as the result of the function execution. FastMCP2's decorator-based approach transforms standard async functions into distributed workflow components by leveraging Docket's dependency injection system. The @MCP tooltask equals true decorator enables asynchronous execution with progress tracking, while the injected progress, current docket, and CurrentWorker dependencies provide clean access to task coordination, worker metadata, and progress reporting. This design maintains separation between business logic and execution concerns, allowing tasks to chain operations via Docket.add while remaining protocol-native MCP background tasks. The trade-off between simplicity and power becomes evident. While raw Asyncio could be used, this approach offers built-in progress tracking, distributed execution, and MCP compliance through a zero configuration in memory, backend for development, or RIDIs for production-scale persistence. The pattern showcases how FastMCP integrates with Docket's workflow engine to enable complex workflow orchestration with maintainable, cleanly separated code.
The docket remembers the worker's name only after the worker forgets to tell it.